Welcome to Haience, where humanity meets science. Tonight we embark on a gentle, mesmerizing journey through one of the universe's greatest mysteries, the invisible tapestry woven by dark matter and dark energy. Imagine a cosmic story hidden between the stars we see, shaping galaxies and guiding the destiny of our universe. Relax, open your mind, and let science and wonder lead you into the profound depths of what we cannot yet see. Here at Haience, we connect the warmth of human curiosity to the cool, endless frontier of scientific discovery. The invisible universe. Picture yourself standing under a vast, dark sky far from city lights. The stars sparkle like scattered jewels, and the Milky Way stretches across the horizon like a glowing river. Each point of light is a star, perhaps with planets, part of our galaxy, which contains billions of stars. Beyond our Milky Way, there are billions of galaxies, each a cosmic city of light. The Hubble Space Telescope has captured images. Like the Hubble Deep Field, showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. It's a breathtaking view, one that feels like peering into infinity. But here's a startling truth: all that you see, the stars, galaxies, and nebulae, makes up less than 5% of the universe. The rest, about 95%, is invisible, composed of two mysterious entities, dark matter and dark energy. These unseen forces shape the cosmos, holding galaxies together and driving the universe's expansion. As astronomer Vera Rubin once said, "We became astronomers thinking we were studying the universe, and now we learn that we are just studying the 5 or 10% that is luminous." This realization is both humbling and thrilling, inviting us to explore a cosmic puzzle. In this video, we'll embark on a journey to understand dark matter and dark energy. We'll explore the evidence that convinced scientists of their existence, from the surprising speeds of stars in galaxies to the faint glow of the universe's earliest light. We'll discuss what these mysterious components might be and how scientists are searching for them. Along the way, we'll share stories of discovery, use simple analogies to make complex ideas clear, and invite you to marvel at the universe's secrets. So, settle in, let your mind wander, and let's dive into the invisible universe. Evidence for the invisible. Despite their invisibility, dark matter and dark energy leave unmistakable clues. Over decades, astronomers have gathered multiple lines of evidence that something unseen is out there. Why do we believe in dark matter? Let's gently explore the key evidence, one piece at a time, like assembling a cosmic puzzle. Galactic rotation curves, the Oort, Zwicky, and Rubin story. Picture a spiral galaxy, a majestic whirl of billions of stars. In the visible disk, stars orbit the galactic center, held in orbit by gravity. According to standard physics, stars on a galaxy's outskirts should orbit much more slowly than those near the center, just as outer planets in our solar system move slower than inner ones because most mass, the Sun, is at the center. However, when astronomers actually measured the speeds of stars in galaxy after galaxy, they encountered a surprise. In the 1970s, Vera Rubin and colleagues observed the Andromeda Galaxy and many others, mapping how fast stars rotated at different distances. They found that stars far from the center were moving just as fast or even faster than stars closer in. The rotation curves were essentially flat,
instead of dropping off with distance.
If the only mass in galaxies was the visible stars and gas, those outer stars should have flown away into space, or the galaxies should have fallen apart. The visible matter's gravity wasn't enough to hold them. Yet the galaxies were stable and spinning too fast for their visible mass. This puzzling result makes sense only if one assumes an unseen mass enveloping each galaxy in a vast halo. In other words, something invisible, dark matter, provides the extra gravity to keep those fast-moving outer stars bound in orbit. To understand how scientists arrived at this point, let's step back in history briefly. As early as 1932, the Dutch astronomer Jan Oort noticed hints of missing mass in our own Milky Way. He studied the motions of nearby stars and found the galaxy's mass, inferred from its gravitational pull, seemed twice as high as the mass of visible stars and gas, suggesting additional unseen matter was present. Around the same time, in 1933, Swiss astronomer Fritz Zwicky made a bolder discovery while observing the Coma cluster of galaxies. He measured the speeds of galaxies buzzing around the cluster's center. They were moving far too fast to be held together by the gravity of the cluster's visible galaxies alone. In fact, Zwicky calculated that the visible matter was only about 10% of the mass needed to keep those galaxies from flying apart. To explain this missing mass, Zwicky coined the term dunkle Materie, German for dark matter. It was a provocative idea that some invisible substance provides most of the mass in clusters of galaxies. Zwicky's results were largely met with skepticism or ignored for decades, partly because the evidence was not yet conclusive and the instruments of the time were limited. By the late 20th century, however, evidence for dark matter had greatly strengthened. Vera Rubin's work in the 1970s was pivotal. With sensitive spectrographs, she measured how stars and gas orbit in dozens of spiral galaxies. Again and again, she observed the same effect. The outer regions of galaxies were rotating unexpectedly fast, indicating far more mass than could be seen. Rubin herself recalled how one galaxy's rotation curve after another came back flat. A clear sign that an unseen mass was present out to the galaxy's edges. Her findings, initially met with surprise, became convincing evidence that Zwicky was right. Dark matter is real. Individual galaxies, but not just clusters, contain huge halos of invisible matter. Rubin's careful work weighed galaxies using their rotation and found they are swathed in about 10 times more mass than all their stars, dust, and gas combined. This was a turning point. The concept of dark matter moved from speculative to mainstream as the best explanation for these dynamical observations. In summary, the unexpectedly high orbital speeds of stars and galaxies, galactic rotation curves, provided one of the first and strongest pieces of evidence for dark matter. The stars are effectively telling us that there is much more gravitational mass present than meets the eye. Without dark matter's extra gravity, galaxies would simply not behave as they do. They'd likely not even have formed in their present stable disks. This is sometimes described as dark matter, acting like a cosmic glue or scaffold, holding galaxies together and allowing them to spin swiftly without flying apart. As we continue, we'll see this glue at work on even larger scales. But first, another line of evidence comes from an elegant prediction of Einstein's general relativity, the bending of light by gravity. Gravitational lensing, weighing the invisible. Einstein's theory of general relativity tells us that mass and energy warp spacetime, causing light to travel along curved paths. This effect, known as gravitational lensing, was first confirmed in 1919 when starlight passing near the Sun was observed to bend during a solar eclipse. In modern times, astronomers use gravitational lensing as a tool to map unseen mass in the universe. Massive objects like galaxy clusters act as cosmic lenses, bending and distorting the light of galaxies far behind them. By observing the distorted shapes or even multiple images of background galaxies, scientists can deduce how much mass is in the foreground lens, and crucially, where that mass is located. What they've found is astonishing. In many cases, the lensing is far stronger than can be accounted for by the visible matter alone. For example, when we weigh a massive galaxy cluster by its lensing effect, we find it has several times more mass than the sum of all its luminous galaxies and hot gas. One detailed NASA analysis put it this way: by measuring how background galaxies are warped by a foreground cluster, astronomers can calculate the cluster's total mass, and it turns out to be more than 5 times greater than the mass in visible stars. Gas and dust. In other words, most of the cluster's mass must be invisible dark matter, dispersed in and around the cluster. This lensing evidence aligns nicely with Zwicky's original missing mass in clusters. But now we observe it directly via the bending of light. Perhaps the most dramatic lensing evidence for dark matter comes from observing colliding galaxy clusters. One famous example is called the Bullet Cluster, 1E0657. 56, the aftermath of 2 galaxy clusters that have recently smashed through one another. In this cosmic collision, the hot gas from each cluster, which is normal matter, slammed into the other and was slowed down, heating up and emitting X-rays. However, the galaxies, mostly empty space, and importantly, the dark matter halos of each cluster sailed right through the collision, with barely a pause. Astronomers mapped the mass distribution in the Bullet Cluster using gravitational lensing, and they found something striking. The bulk of the mass is not where the X-ray emitting gas is concentrated, pink regions, but rather ahead of it, around the locations of the galaxy distributions. In other words, the dark matter kept going and separated from the normal matter during the collision, because dark matter particles, whatever they are, hardly interact except through gravity. The Bullet Cluster is unusual in that it let us see dark matter and normal matter part ways during a collision, providing direct evidence that dark matter is a separate component that doesn't collide or slow down like gas does. This observation cannot be explained by modifying gravity alone, something real and massive, but invisible, was clearly left on its own path. Gravitational lensing with examples like the Bullet Cluster thus provides a visual confirmation of dark matter's existence and location. Clusters of galaxies, which are the largest gravitational structures in the universe, are dominated by dark matter. In fact, astronomers estimate that galaxy clusters have roughly 5 to 6 times more dark matter than normal matter overall. Lensing maps show clumpy concentrations of dark matter within clusters, often enveloping the individual galaxies and extending well beyond. These maps beautifully illustrate dark matter's role as the scaffolding of galaxy clusters. We now have three independent lines of evidence for dark matter: galaxy rotation speeds, motions of galaxies in clusters, and gravitational lensing, all pointing to the same conclusion. But there's more. Even the relic light from the early universe and the grand pattern of galaxies across cosmic space bear the fingerprints of dark matter. The cosmic microwave background, a baby picture of the universe. Let's step back to a very early time, about 380,000 years after the Big Bang. At that time, the universe was a hot, dense soup of plasma. As it expanded and cooled, it reached a point where electrons combined with protons to form neutral atoms. And suddenly, the fog cleared. Light was free to travel. The glow from that moment is still around us today, stretched to microwave wavelengths by 13.8 billion years of expansion. We call it the cosmic microwave background, CMB, essentially the afterglow of the Big Bang, a faint microwave light coming from all directions in space. If we map the CMB across the sky, we see it as mostly uniform, but with tiny variations, hotter and colder spots at the level of only millionths of a degree. These spots correspond to slightly different densities in the early universe. The seeds of future galaxies and clusters. They are a baby picture of the universe, encoding a wealth of information about the cosmos's contents and structure. By carefully analyzing the pattern of these CMB fluctuations, scientists can infer how much of the universe was in the form of ordinary matter, dark matter, and other components at that early time. Satellites like WMAP and Planck have measured the CMB with exquisite precision. The results are striking. The CMB data indicate that normal baryonic matter makes up only about 1/6 of the total matter, while the rest, about 5/6 of the matter, must be non-baryonic dark matter. In other words, about 84% of the matter in the universe was and is dark matter, with only 16% ordinary matter. These proportions align exactly with what's needed to explain galaxy rotation curves and cluster lensing, and also match the Big Bang nucleosynthesis predictions for how much ordinary matter, like hydrogen and helium, should have formed. The CMB analysis essentially confirms the presence of dark matter from the time the universe was very young, long before galaxies even existed. This is a powerful, independent check. Even if we had doubts from galaxy measurements, the universe's earliest light insists on the existence of dark matter to make the patterns we observe. Without dark matter's extra gravity in the early universe, the primordial hot and cold spots in the CMB would have a different character. The gravity of dark matter helped seed deeper wells that ordinary matter later fell into. The fact that our CMB observations fit a model with 27% dark matter and 25% normal matter by cosmic energy content is a major triumph for the dark matter paradigm. In summary, the CMB is like a blueprint. By studying its faint patterns, scientists have measured the recipe of the universe. That recipe tells us dark matter was already influencing the infant universe, helping matter clump and eventually form galaxies. It's awe-inspiring to realize that even in that first light of the cosmos, we see the gravitational imprint of something invisible that outweighs the ordinary matter 5 to 1. Large-scale structure, the cosmic web and dark matter's role. From the CMB's tiny ripples over billions of years, grew the vast cosmic web of galaxies we see today. Galaxies are not distributed randomly. On very large scales, they form a wispy web. Filaments and clusters of galaxies interspersed with huge, near-empty voids. How did this intricate structure arise? Computer simulations of cosmic structure formation have given us a clue. Dark matter is the key ingredient that shaped the cosmic web. In the early universe, dark matter, which does not feel pressure from light, as ordinary plasma does, began to clump under its own gravity, forming a loose framework or scaffold. Ordinary matter, gas, slowly fell into the gravitational wells of that dark matter scaffold once the universe cooled enough. Over time, the gas collected and formed stars and galaxies in those dense regions. Thus, galaxies formed along the filaments of dark matter, like sparkling beads on invisible strings. This theoretical picture has been borne out by observations and large supercomputer simulations. The universe's large-scale structure simply cannot be explained without dark matter's gravitational pull organizing the early matter. Galaxy clusters formed where filaments of dark matter intersected, creating deep gravity wells. If we try to simulate structure formation with only normal matter, the result is a universe with far less clustering by the present day. It doesn't match what we observe. The galaxies would be more diffuse and take much longer to coalesce. Dark matter, being abundant and cold, slow-moving, provided the gravitational scaffolding for structure to grow faster. Astronomer Richard Massey described dark matter as the scaffolding inside of which stars and galaxies have been assembled over billions of years. We have even managed to map some of this cosmic dark matter distribution. For instance, studies using Hubble Space Telescope observations through weak gravitational lensing of distant galaxies have produced 3D maps of dark matter in patches of the sky. These maps reveal a network of dense clumps and filaments of dark matter extending across hundreds of millions of light years, with galaxies and clusters forming at the densest nodules, exactly as the theory predicts. One such map from the Cosmos survey showed that where we see a cluster of galaxies, there is a huge concentration of dark matter, and between clusters, there are dark matter filaments along which smaller groups of galaxies align. It is profoundly elegant. The dark matter shaped the cosmic landscape, and the luminous matter merely paints the highlights where dark matter drew the outlines. Another piece of evidence in this vein is the timeline of structure formation. We see very distant young galaxies with mature structures, and we see galaxies clustering into groups and clusters relatively early in cosmic history. If dark matter were not present, or if it were a different kind, like hot, fast-moving particles, then don't add gravity. The formation of galaxies and clusters would have been delayed. For example, fast-moving neutrino-type dark matter, hot dark matter, would stream out of small overdensities, preventing them from growing. Resulting in only very large structures forming much later, a top-down formation scenario. But our universe shows signs of early small-scale structure, dwarf galaxies, etc., implying dark matter must have been cold or slow-moving, able to clump on small scales early on. A bottom-up scenario. Indeed, observations of the oldest stars and galaxies, as well as the CNB, indicate that the first stars formed quite early, something that would be hard to achieve without dark matter's help, drawing matter into star-forming halos. Fast thermal motions, like those of light particles or neutrinos, would have smoothed out density fluctuations. But the fact that fluctuations survived on small scales is evidence that dark matter is heavy and moves slowly, hence cold. The success of the lambda CDM model, cold dark matter with a cosmological constant, in explaining both the CNB and large-scale structure growth is a major reason scientists are confident in dark matter's existence. To summarize this evidentiary journey, we have converging evidence from galaxy rotation behavior, galaxy cluster dynamics, gravitational lensing maps, the cosmic microwave background, and the large-scale distribution of galaxies. All lines of evidence independently point to the same conclusion. The universe contains a huge amount of unseen mass, dark matter, roughly 5 times more than ordinary matter. This dark matter interacts via gravity, influencing the motion of galaxies and light itself, yet it hardly interacts with light or normal atoms in any other way, which is why it's so elusive. By contrast, dark energy's evidence comes from an entirely different set of observations, which we'll discuss later, notably the accelerated expansion of the universe. For now, having established why scientists are convinced dark matter exists, let's delve into what this dark matter could actually be, and what dark energy might be as well. We stand at the edge of known physics. The evidence demands new ingredients, and our task is to identify them. This quest is ongoing, and as we shall see, it has spurred some of the most ambitious experiments and imaginative theories in modern science. The what? Hypotheses of the unseen. Having gathered the clues, we now ask, what is dark matter and what is dark energy? These questions are challenging, akin to solving a mystery when 95% of the culprit is invisible. Scientists have brainstormed many possibilities and tested several over the years. Let's explore what we know dark matter is not, then discuss leading theories of what it might be. After that, we'll touch on dark energy's possible nature. What dark matter is not, ruling out the obvious. When the missing mass problem first emerged, one might have thought, perhaps it's just ordinary matter we failed to see, like faint stars, dead stars, black holes, or clouds of gas lurking in space. A reasonable guess. However, decades of observations and calculations have largely ruled out normal matter as the main form of dark matter, not ordinary atoms or gas. If dark matter were made of protons, neutrons, and electrons, the stuff of atoms, it would be baryonic matter. But we have very strong evidence that the total amount of baryonic matter in the universe is limited. For one, calculations of Big Bang nucleosynthesis, how hydrogen and helium formed in the early universe, and the precise measurements of the CNB tell us that only about 4 to 5% of the universe's content can be ordinary matter. If there were a lot more, the proportions of light elements and the CMB anisotropies would not match what we see. Thus, the bulk of dark matter cannot simply be hidden clouds of hydrogen or unseen stars, because that would overshoot the allowed baryon budget. Furthermore, if there were massive amounts of unseen gas or dust, we might detect it through its absorption of starlight, its emission of infrared or X-ray radiation, or other signals. Surveys indicate that while there is some missing baryonic matter, e.g., diffuse gas in intergalactic space, it's not nearly enough to account for the gravitational effects attributed to dark matter. In summary, dark matter is non-baryonic, something other than normal atomic matter. Not just dim stars or black holes in bulk. Could dark matter be watts of faint stars, brown dwarfs, failed stars? Or massive black holes scattered through galactic halos? This idea was investigated through searches for so-called machos, massive compact halo objects. Astronomers used a technique called gravitational microlensing. If a dark object, like a faint star or black hole, passes in front of a background star, its gravity can momentarily brighten the star. Over the 1990s and 2000s, experiments like EROS and MACHO monitored millions of stars in the Magellanic Clouds and our galaxy's bulge to catch such lensing events. They did find a few, indicating some fraction of the halo is made of dim objects, but not nearly enough. The results showed that such objects could contribute, at most, about 20% or even less of the Milky Way's dark matter. Certainly not all of it. For example, brown dwarfs, too small to shine like stars, were a prime suspect, but Hubble Space Telescope deep observations failed to find the huge population that would be needed. Stellar remnants like white dwarfs or neutron stars also cannot account for the majority of dark matter. They would produce more light or gravitational disturbances than observed if present in the required numbers. What about black holes? Ordinary stellar mass black holes are rare, formed from dying stars, and not enough in number. Primordial black holes, hypothetically formed in the early universe, were also considered, and we'll mention them later. But a wide range of masses for primordial black holes have been constrained by various observations, including lensing and gravitational waves. So far, there's no evidence that dark matter is primarily black holes. The data instead point away from this option, except possibly in narrow mass ranges. In short, astronomers looked for all manner of hidden normal objects, faint stars, cold gas, dark planets, black holes, and found that none of these can account for the missing mass. The cosmos's dark matter seems to be something fundamentally different. Not large, modified gravity theories like MOND, modified Newtonian dynamics, or other extensions of general relativity attempt to explain galaxy rotation curves and other phenomena without dark matter by tweaking how gravity works at low accelerations or large scales. These theories can fit some galaxy rotation data, but they struggle to explain the full suite of evidence. For instance, MOND doesn't naturally explain the bullet cluster's separation of mass and normal matter, or the precise CMB pattern, without invoking something like neutrinos as dark matter, which then reintroduces unseen mass. While research on alternative gravity continues, the simplest and most comprehensive explanation so far is indeed an unseen mass component. It's worth noting, the prevailing view among most astronomers and physicists is that dark matter is real stuff, not just a mirage from modified gravity, because one theory, dark matter, explains all the disparate observations consistently, whereas modified gravity would need to be rather contrived to explain things like the CMB and cluster lensing simultaneously. So while we remain open-minded, the working assumption is that dark matter exists as a form of matter. Thus, by elimination, dark matter is not ordinary atoms, not stars or gas, and not explained by any known objects or simple tweaks. It must be something new, something that doesn't interact with light, hence dark, doesn't collide or clump in the usual way. This leads us to consider exotic particles. For decades, physicists have proposed that dark matter could consist of one or more types of new fundamental particle outside the standard model of particle physics. Cold dark matter, the leading theory. The evidence from structure formation tells us that dark matter must be cold, meaning the particles were moving much slower than light in the early universe, as opposed to hot dark matter, which would move at relativistic speeds and erase small-scale structures. Let's discuss the leading candidates. Cold dark matter, CDM, fits the observations. It would clump early, forming small halos that merge into larger ones, a bottom-up growth of structure, matching what we see in the galaxy distribution and CMB. So, virtually all leading candidates for dark matter are cold, or at most warm, which is intermediate. We also know dark matter is non-baryonic, as discussed. The lambda CDM model, which is our standard cosmological model, includes cold dark matter as about 27% of the universe and has been immensely successful in reproducing observed structures and CMB data. In this model, dark matter interacts via gravity and possibly the weak nuclear force, but not electromagnetism, hence it doesn't absorb light. Cold dark matter particles would form a roughly spherical halo around galaxies. Near the centers, their density is highest, helping hold rotating stars in orbit. Farther out, the halo provides the gravity to keep gas and outer stars bound. Because these particles don't collide or stick together, no electromagnetic interaction, they can form these extended halos rather than flattening into disks, unlike normal gas, which cools and settles into disks. Dark matter stays more puffed out in a halo. This picture explains why galaxies have extended unseen mass and why galaxy clusters have dark matter spread through them without radiating energy away. In summary, the hypothesis is that dark matter is some new, stable elementary particle or family of particles created in the early universe that has mass, hence gravity, but interacts extremely weakly with other matter and light. Now let's talk about a couple of the main particle candidates that scientists have been excited about. Leading candidates for dark matter particles. 1. WIMPs. Weakly interacting massive particles. For a long time, front-runner candidate was the WIMP. As the name suggests, a WIMP would be a heavy particle, massive, that interacts via the weak nuclear force and gravity, of course, but not via the electromagnetic force. If such particles were born in the hot Big Bang, they would naturally linger today in just the right amount to be dark matter if their mass and interaction strength are around a certain scale. This remarkable coincidence is sometimes called the WIMP miracle. Stop there. A particle of mass on the order of 100 GeV, about 100 times the proton's mass, with roughly weak force interactions, would produce roughly the correct abundance of dark matter in the early universe when it froze out of thermal equilibrium. It was a very compelling hint that new physics like supersymmetry could predict a stable WIMP, such as the neutralino, the lightest supersymmetric particle that would serve as dark matter. WIMPs fit nicely into many extensions of particle physics theories, and they'd be cold, moving non-relativistically after the early universe. For these reasons, WIMPs became a prominent dark matter candidate and have been the target of many experiments. The classic WIMP would have about the mass of a heavy atom or even heavier. Dot. And one teacup's worth of space might contain perhaps a few WIMPs passing through at any moment without you noticing. They would be all around and through us, but ghostly. WIMPs might occasionally bump into atomic nuclei, very rarely, which is the principle behind direct detection experiments. More on that soon. Despite a long, ongoing search, no definitive WIMP has been found yet, which has started to dim the allure of the miracle slightly. But WIMPs are still very much in play in certain mass ranges or with more complex interaction properties. It could be that if WIMPs exist, their interactions are even weaker or their masses higher than initially expected, making them harder to detect. Or nature might have chosen a different form for dark matter. Axions. Another intriguing candidate is the axion, a hypothetical ultralight particle proposed originally to solve a completely different problem in particle physics, the strong CP problem in quantum chromodynamics. Q. Axions were postulated in the late 1970s by Roberto Peccei and Helen Quinn's theory, and named by Frank Wilczek after a laundry detergent brand, playfully because they cleaned up a problem in theory. Axions, if they exist, could also be produced in the early universe in great numbers. Unlike WIMPs, axions would be extremely light, perhaps a billionth of an electron's mass or even lighter. But if they are that light, they would also be extremely numerous and form a kind of cold Bose-Einstein condensate background. Despite being light, axions can act as cold dark matter if they were born not in thermal equilibrium, but through a field process in the early universe. Essentially, they would behave like a classical field oscillating that contributes mass density. One appealing aspect is that axions would be so light that they are cold in the sense that quantum uncertainty gives them a very long wavelength, tot, which can inhibit them from clustering on tiny scales, potentially addressing some small-scale distribution puzzles. Axions also interact very weakly, but they have a unique possible signature. They can sometimes convert into photons, and vice versa, in the presence of a magnetic field. Experiments are underway, like ADMX, Axion Dark Matter Experiment, to detect axions by using strong magnetic fields to try to induce this conversion and listen for a faint radio signal. As of now, no conclusive axion detection. But the search is ongoing. Axions have gained popularity especially as some other candidates remain elusive. If an axion's mass is right, a few microelectron volts, for instance, it could be exactly what dark matter is made of. 3. Sterile neutrinos and other candidates. There are many other ideas, too. Sterile neutrinos are a type of neutrino that doesn't interact via the weak force, like regular neutrinos do. Essentially, a neutrino that only feels gravity. If such particles exist with the right mass, Kevin's scale, they could be dark matter, probably warm dark matter in that case. There have been some tantalizing signals, like an unexplained X-ray emission line in galaxy clusters that some have speculated could be due to sterile neutrino decay. But it's far from confirmed. Another concept is an entire hidden sector of particles, dark photons, dark forces, etc. A whole mirror world of particles that mostly don't mix with our regular particles, except perhaps a little.
This might sound extravagant, but it's a possibility being tested in various ways. Primordial black holes, PBHs, have also seen a resurgence in interest, especially after LIGO started detecting black hole mergers. Some people noted the masses LIGO detected, 30-ish solar masses.
Could hint at PBHs. However, there are many constraints on PBHs from various observations, gravitational lensing surveys, cosmic microwave background, etc., and it seems unlikely that all dark matter is PBHs. Though a small fraction could be, we mention PBHs here for completeness. They would be cold and act like particle-like matter in gravitational terms, but they're not a particle physics solution, rather a cosmological relic scenario. In essence, the leading paradigm remains that dark matter is likely some new, stable particle that was produced in the early universe and has survived to the present, swirling around galaxies and clusters. Whether it's a heavy WIMP or an ultra-light axion or something else entirely, we don't yet know. But the hunt for the dark matter particle or particles is one of the biggest quests in physics today. In the next section, we'll discuss how scientists are searching for these elusive particles, listening for their whispers in deep underground labs, watching for their effects in space, and even trying to create them in high-energy collisions. Before moving on, it's worth emphasizing a beauty here. The concept of dark matter ties together the very small, particle physics, with the very large, cosmic structure. It shows how the universe at its grandest scale may be governed by the properties of tiny particles we have yet to discover. There's a profound unity in figuring this out. We're doing experiments in our laboratories to understand why galaxies rotate as they do, and how the cosmic web formed. It's a reminder of how interconnected physics is, across vast scales. Now, let's talk about those searches in more detail. The how. The search for dark matter. Unveiling dark matter's identity is a bit like trying to catch a shadow. It doesn't emit light. It slips through us silently, but scientists are clever and have devised several strategies to detect dark matter indirectly or directly. We often categorize the search into 3 approaches, whimsically summarized as shake it, break it, or make it. In other words, direct detection, shake it. Try to catch a dark matter particle shaking an atomic nucleus here on Earth. Indirect detection, break it. Look in space for signs of dark matter particles annihilating or decaying, which could break into normal particles like gamma rays or cosmic rays that we can detect. Collider production, make it. Smash known particles together at high energy, like in the Large Hadron Collider, to hopefully create dark matter particles out of pure energy, E equals mc squared. If successful, they'd escape the detector unseen, but their presence would be inferred from missing energy. Let's explore each of these search methods and where they stand, and then briefly mention a 4th frontier, gravitational wave astronomy, which might provide new avenues for dark matter research in the future. Direct detection experiments, listening for dark matter's whisper. Imagine a very quiet underground laboratory, deep beneath the Earth's surface, shielded from the noisy hustle of cosmic rays and radiation. In this calm, silent environment sits a large, ultra-sensitive detector. For example, a tank filled with several tons of pure liquid xenon, kept in the dark. The scientists wait patiently because, once in a very long while, a dark matter particle from the halo of our galaxy might drift through and strike a xenon atom's nucleus, imparting a tiny kick. When that happens, the xenon atom will recoil and produce a faint flash of light and some ionization. A whisper of a signal that the detector can register. This is the essence of direct detection. We are trying to feel the billiard ball collision of a dark matter particle with normal matter, even though such collisions are exceedingly rare. Detectors like Lux Zeppelin LZ in the USA, Xenon NT in Italy, Panda X in China, and others are among the most sensitive devices ever built. To reduce false signals, they are placed deep underground. For instance, LZ is nearly a mile underground in South Dakota to filter out cosmic rays, the constant shower of high-energy particles from space that would overwhelm the experiment if on the surface. It's like listening for a pin drop at a rock concert. You need to get far away from the noise or shield it out. Underground, surrounded by rock, plus additional shielding and using radio-pure materials, the background noise is greatly reduced. The detectors are also equipped with Veeder systems to reject events caused by stray radiation or neutrons. They become sanctuaries of silence where we hope to hear the gentle knock of a dark matter particle. How do they work? Let's take the example of LZ, one of the most advanced direct detection experiments, a successor to earlier LUX. LZ is essentially a large thermos bottle containing 7 to 10 tons of liquid xenon. Xenon is used because it's heavy, so a nucleus provides a big target, and very pure. It also scintillates, produces light, when energy is deposited. If a dark matter particle, say a WIMP, hits a xenon nucleus, two things happen. The nucleus recoils, like a billiard ball struck by another, and in doing so, it emits a faint flash of ultraviolet light and knocks loose some electrons. In LZ and similar dual-phase xenon detectors like Xenon NT, there are photomultiplier tubes watching for that flash, called S1 signal. The freed electrons are drifted by an electric field to the top of the tank, where they enter a thin gas layer and produce another flash, S2 signal. By measuring these, scientists get the energy of the event and can even localize where in the detector it happened by timing and light pattern. To give you an idea of scale, these experiments are so quiet that maybe only a few candidate interactions per year might occur in the whole detector if dark matter is around the expected cross-section. They then carefully analyze if the event looks like a nuclear recoil, what a WIMP would cause, or an electron recoil, more likely from residual radioactivity or other background. They are searching for something incredibly subtle, one interaction in 10 to the 25th or so particles per year. It's a patience game, requiring years of data, ultra-clean conditions, and cutting-edge technology. The sensitivity has improved by orders of magnitude over the last couple of decades. What have they found? So far, no confirmed dark matter hit. Experiments like Lux, Xenon 1T, and its upgrade, Xenon NT, Panda X, and now LZ have all reported essentially no results, which is not a failure, but important information. It means that if WIMPs exist, their probability of hitting a nucleus, their cross-section, must be below certain very tiny limits. Otherwise, we would have seen them by now. For example, LZ's first run in 2022 to 2023 set the best limits yet on WIMP interactions, further shrinking the hiding space for the classic WIMP. This has already ruled out some simpler WIMP models and helped guide theorists. Maybe WIMPs... if real, interact in more complex ways or lie at higher masses than we can easily detect yet. It's worth highlighting how researchers describe it. We didn't detect dark matter, but we have constrained its properties. Each null result is like narrowing down the suspects in our cosmic mystery. And the quest isn't over. Far from it. New detectors are being planned and built, with even larger masses of xenon or argon, and improved techniques to go yet another order of magnitude down in cross-section sensitivity. It's a game of leapfrog with the unknown. Maybe the dark matter interactions are just a bit weaker than current sensitivity, and the next generation experiments will catch them. We should also mention that there have been a few intriguing anomalies reported. For example, the Dama Libra experiment in Italy long claimed a yearly modulation in their detector that they attribute to Earth moving through the dark matter halo, though other experiments have not confirmed this. And Xenon 1T once saw an excess of low-energy electron recoils that got people talking about axions or unknown backgrounds. None of these anomalies have risen to the level of a clear dark matter detection widely accepted. They remain puzzles or likely unrelated to dark matter. It hasn't happened yet in a definitive way, but the experiments are marvels of engineering and are inching closer to the limits where even neutrinos, which do occasionally hit nuclei, will become a background, the neutrino floor. So direct detection is a bit like waiting in a dark, silent room for a barely perceptible tap on the shoulder. If dark matter interactions are below that, it will be extremely challenging to detect them in this manner. But we're not there yet, and new ideas like directional detectors able to sense the direction of the recoil, which could indicate a dark matter wind direction, are also being explored. The direct detection quest continues with a fervent hope that one night or day, in those deep mines, a dark matter particle will finally announce its presence with a tiny flash of light in a tank of xenon. Ending a decades-long search, indirect detection, signals from the cosmos, the universe itself can act as a detector too. If dark matter particles can annihilate each other, as many theories suggest for WIMPs, where a particle and its antiparticle or two particles can annihilate into standard particles, or if they can decay on very long timescales into lighter particles, we might see the byproducts of those processes in space. This approach is called indirect detection. We look for excesses of high-energy particles or radiation coming from regions with lots of dark matter. What kind of signals? A popular one is gamma rays. Very high-energy light, photons, that can travel from distant regions to us. If dark matter annihilates, one possible channel is it produces a pair of photons or other particles that then produce gamma rays. We expect the highest chances of annihilation where dark matter density is highest, because two particles have to find each other. That means the centers of galaxies, especially the center of Milky Way. Or in small satellite galaxies, dwarf spheroidals, which are very dark matter rich and have low background from other sources. So, scientists have pointed instruments like the Fermi Gamma Ray Space Telescope at these targets. The Galactic Center is a prime region. Our own galaxy's core has a high density of dark matter. Intriguingly, analyses of Fermi data have shown a gamma-ray excess in the galactic center. Basically, after subtracting all known sources and diffuse emissions, There's some extra glow of gamma rays at energies around a few GeV that wasn't expected. This excess has a spherical distribution somewhat consistent with a dark matter annihilation profile, and a spectrum energy distribution that could fit certain WIMP models. For a while, this was touted as a possible dark matter signal. However, there are alternative explanations, notably a population of unseen millisecond pulsars, rapidly spinning neutron stars, could also produce a similar gamma excess. It's tricky to distinguish. As of now, the jury is still out. The galactic center GeV excess might be hinting at dark matter, but it might also be astrophysical. Moreover, if it were dark matter annihilation, one might expect similar signals in other places. Scientists have looked at dwarf spheroidal galaxies, small satellite galaxies orbiting the Milky Way that are very dark matter-dominated and have few other gamma sources. So far, Fermi's observations of dwarfs have not found any gamma excess, and B's non-detections put stringent limits on the annihilation cross-section, how strongly dark matter particles self-annihilate. In fact, the limits are strong enough that if the galactic center excess were due to dark matter, it would be somewhat in tension with what dwarfs show, unless the dark matter distribution or other factors are different. This leads some to suspect the excess is more likely pulsars or some effect of the complicated galactic center environment. Nonetheless, the indirect search goes on. Besides gamma rays, detectors look for cosmic rays, high-energy electrons, positrons, antiprotons, etc., that could result from dark matter annihilations. The AMS-02 experiment on the International Space Station, for example, measured an excess of high-energy positrons, anti-electrons, in cosmic rays. Could that be dark matter? Some models of heavy dark matter annihilating could produce positron excesses, but pulsars can also accelerate positrons. It remains inconclusive. The positron excess, observed also by earlier Panelite experiment, is interesting, but not a smoking gun. Similarly, searches for an excess of antiprotons or gamma ray lines. A sharp spectral line would be a clearer DM annihilation signature since few astrophysical processes give lines have been conducted. There was a tentative hint of a 30 GeV gamma ray line in Fermi data years ago that caused excitement, but it faded with more data and scrutiny, likely an instrumental artifact. Another messenger? Neutrinos. If dark matter accumulates in places like the Sun's core, WIMPs can lose energy by scattering and be captured by the Sun's gravity over time. They could annihilate in the Sun and produce neutrinos, since other particles would be absorbed. Large neutrino observatories like IceCube in Antarctica have looked for an excess of neutrinos from the Sun or Earth's core that might indicate WIMP annihilation. So far, nothing significant detected on that front either, which again places limits on interaction strengths. Overall, indirect detection has not yielded a confirmed discovery of dark matter, but it provides very valuable constraints and a few tantalizing cosmic rays and gamma ray clues that keep theorists busy. It's like looking for a faint smoke signal in a vast sky of fireworks. The universe has many energetic processes that produce gamma rays and cosmic rays, so teasing out a dark matter signal is challenging. If dark matter particles are lighter in mass, like below GeV, they might produce signals outside Fermi's main sensitivity or in different channels. If they're heavier, they might produce very high-energy gamma rays or neutrinos that upcoming telescopes and arrays, like the Cherenkov telescope array for gammas. One exciting development is the use of multi-messenger astronomy, combining data from different types of signals, and also new targets, like looking at galaxy clusters in X-rays for decays. Some claimed a possible 3.5 keV X-ray line common in many clusters, which could be a decaying sterile neutrino, again disputed. Or KM3 net for neutrinos could detect. We're covering a lot of ground, but the take-home point is indirect searches cast a wide net across the sky for any unusual emissions that could be the glow of dark matter particles meeting their end. We have some hints, but no confirmed catch yet. As our instruments get better and our sky surveys accumulate more data, we might eventually catch sight of dark matter's shadow in these high-energy signals. Collider experiments, creating the invisible. The third approach is to simulate the conditions of the early universe in the laboratory, i.e. high-energy particle collisions, and see if we can produce dark matter particles on demand. A prime facility for this is the Large Hadron Collider LHC at CERN, the world's most powerful particle accelerator. The LHC accelerates protons to mere light speed and smashes them together at enormous energies, currently 13 TeV, possibly higher in future runs. In such collisions, energy can convert into mass in the form of particle-antiparticle pairs. The idea is, if there is a heavy dark matter particle, maybe once in a while an LHC collision will produce some of them. They would likely be stable, at least on detector timescales, and would interact so weakly that they'd fly out of the detector without leaving a trace, quite literally invisible to our apparatus, which typically detects charged particles or energy deposited. So how do you know they were produced? By momentum conservation. If two protons collide and you detect a spray of standard particles going one way, but notice an imbalance, missing momentum in the opposite direction, that can indicate something unseen took away momentum. The classic signature is called missing transverse energy because initial protons come along the beam axis. Net momentum perpendicular to the beam should be zero. If it's not, we infer a non-detected particle carried it off. So LHC dark matter searches often look for events like monojet or monophoton events. One jet of particles or one photon recoiling against nothing. For example, one proton collision produces a high-energy quark that manifests as a jet, and perhaps a dark matter particle on the other side. The jet is detected, but balancing it is missing momentum equals potential dark particle. They also look in supersymmetry searches for signs of the lightest supersymmetric particle, often stable, which would be a DM candidate, being produced in cascades, again leading to missing energy plus other visible stuff. Despite a multitude of searches, so far the LHC has not seen any direct sign of dark matter particles. Every time they see missing energy, it can be attributed to neutrinos, which are known particles that also escape detectors, or is within the expected background. They have put limits on certain models. For instance, if a WIMP had been, say, 100 GeV with moderate interaction strength, the LHC might have made it, but none appeared clearly. This absence of new particle discovery at the LHC, not just dark matter, but also no supersymmetry seen yet in general, has constrained many theories. However, There is a huge range of possibilities for dark matter mass. It could be too heavy for LHC, like several TeV or more. Point 5. End of explanation, which would be harder to produce in significant numbers, or it could have very feeble coupling, so it's produced too rarely to notice. Future colliders or upgrades might push further. Also, sometimes dark matter might come out not completely invisibly. E.g., if it's part of a hidden sector, maybe it decays into slightly visible things after a short delay, leading to unusual detector signatures like displaced vertices or exotic particle tracks. So collider physicists are broadening their search strategies. One very interesting possibility is if dark matter is related to the Higgs boson. The Higgs could sometimes decay into dark matter particles invisibly. Experiments have looked for an invisible decay fraction of the Higgs and have so far not seen anything significant. Meaning, if Higgs decays to dark matter, it's less than about 15 to 20% of the time. The bottom line for colliders is we haven't found dark matter yet, but we've narrowed down many of the regions where the particle may lie hidden. This forces theorists to refine models. It could be the dark matter particle is simply beyond the current reach, or interacts in a way that makes it hard to produce. The LHC will continue to run and upgrade. And there are proposals for future more powerful colliders, like a future circular collider or a high-energy linear collider that could expand the search. It's a bit like fishing in a vast and dark sea. We have not caught the big fish yet, but each improvement in our nets, energy, intensity, detection techniques, gives another opportunity. An important synergy if one of the approaches, direct, indirect, ... or collider, sees something, the others can cross-check. For example, if LHC found a particle that could be dark matter, we would expect to also perhaps see its annihilation signals in space or catch it in detectors. With appropriate relations between masses and cross-sections, the search for dark matter is truly multidisciplinary, spanning astrophysics, detector engineering, and high-energy physics. It's a global effort. Gravitational wave astronomy, brief mention, future prospects. A more futuristic or less developed avenue is the idea of using gravitational waves, ripples in space-time, to probe dark matter. With the advent of LIGO and Virgo detecting black hole mergers, stop. Some scientists have thought about whether dark matter could affect gravitational wave signals, or whether some gravitational wave sources might be dark matter objects. For instance, if dark matter includes primordial black holes, their mergers would be detected by LIGO. So far, LIGO's black hole merger rates and masses haven't strongly indicated a need for primordial black holes as the majority of dark matter, but they do give some constraints. As gravitational wave detectors become more sensitive, and future ones like Einstein Telescope or LISA come online, they could potentially detect signals from exotic compact dark objects or capture subtle effects like gravitational wave lensing by clumps of dark matter. There are proposals to use pulsar timing arrays which detect gravitational waves of very low frequency to see if dark matter perturbs the signals or contributes to a stochastic background. Another idea: if certain dark matter candidates like axions form macroscopic condensates or structures, they might give off gravitational wave bursts when they collapse or interact. This is quite speculative at this stage. However, it's wonderful that even in this new window of gravitational waves, People are thinking of ways it could shed light on dark matter or dark energy, e.g., gravitational waves could eventually probe the expansion of the universe in ways that inform dark energy studies. So, while gravitational wave astronomy is still new, it's worth noting that the quest for dark matter may eventually tap into these cosmic vibrations as well. We might imagine future observatories hearing the hum of dark matter through subtle gravitational effects. In any case, it's a reminder that as technology advances, new methods to hunt dark matter keep emerging. To recap this section, humanity is throwing everything and the kitchen sink at the dark matter problem. Deep mines, space telescopes, particle colliders, and even gravitational wave detectors. It's a grand hunt. And while we haven't caught the beast yet, each method has pushed the bounds of knowledge and will continue to do so. It's quite possible that in the next decade or two, one of these approaches will succeed, and we'll finally learn what dark matter is. The moment of discovery will be monumental, shining light, perhaps metaphorically, on the dark side of our universe. Until then, the search continues, quietly in underground labs, vigilantly in the sky, and powerfully at colliders, even as you listen to this in the tranquility of the present moment. The puzzle of dark energy. After grappling with dark matter, we turn to dark energy, an even stranger puzzle in many ways. If dark matter is the universe's hidden mass, dark energy is like a hidden force or energy of space itself. It's the dominant component, making up about 2/3 of the cosmic energy budget. And it's responsible for one of the most shocking discoveries in modern astronomy, that the expansion of the universe is accelerating. Let's break down the story of dark energy, how we found it, a tale of exploding stars and unexpected results, what it might be, cosmological constant or a new field, and why it's such a deep mystery, the infamous cosmological constant problem, all in a calm, reflective manner. The expanding universe and Hubble's law, recap of key concepts. In the early 20th century, our understanding of the cosmos underwent a revolution. Edwin Hubble observed distant galaxies, then called nebulae, and found that their light was redshifted. They appeared to be rushing away from us. In 1929, Hubble published his observations, showing that the farther a galaxy is, the faster it is receding. This is Hubble's law. It revealed that space itself is expanding, carrying galaxies apart like raisins in a rising loaf of bread. The universe, once thought static, was actually dynamic and growing larger over time. At first, everyone assumed this expansion set forth by the Big Bang must be slowing down over time. After all, gravity pulls matter together over billions of years, ... A gravitational attraction of everything in the universe on everything else should be putting the brakes on the expansion. It was thought that maybe the expansion would slow to a stop and reverse, big crunch, or slow and asymptotically approach a halt, or slow but never quite stop, depending on how much mass the universe has. In fact, measuring the rate of slowdown, the deceleration, was a big goal for cosmologists by the late 20th century.
Because it would tell us the fate of the cosmos and how much matter there is, no one seriously considered that the expansion might be speeding up. That just wasn't in the standard picture, unless one resurrected Einstein's cosmological constant.
which Einstein himself had set aside as a blunder after Hubble's discovery of expansion. Accelerated expansion, the Nobel Prize discovery. Now we come to the late 1990s. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were racing to measure the deceleration of the universe by observing Type 1a supernova. These are exploding stars that have almost uniform intrinsic brightness. Thus, they act as standard candles for measuring cosmic distances. By comparing their known luminosity to their observed brightness, one can get their distance. By measuring their redshift, one gets how fast they're receding. This allows mapping the expansion rate at different times in the past. What they found was completely unexpected. The distant supernovae were dimmer than they should have been if the universe's expansion was slowing down. Dimmer meant they were farther away than anticipated given their redshift. In 1998, the teams announced that the expansion of the universe isn't slowing, it's speeding up. This was often described with astonishment. One analogy? It's as if you threw a ball up in the air, expecting gravity to slow it and bring it back down. But instead, it started rising faster and faster toward the sky. The discovery was so momentous that it earned the 2011 Nobel Prize in Physics for the team leaders, Saul Perlmutter Andrees, Brian Schmidt, and Adam Rees. Let's take a moment to appreciate how shocking this was. The data showed that the universe, after about 9 billion years of expansion, started accelerating. We often date the onset of acceleration to around 5 billion years ago, which coincidentally is when our Sun and Earth formed, so we live in an accelerating universe era. Some new effect had to be counteracting gravity on large scales, some kind of repulsive gravity or pressure in the fabric of space. This mysterious agent was dubbed dark energy, a term coined by cosmologist Michael Turner around 1998. It is dark because we can't see it or touch it, and energy because it seems to be a property of space that drives acceleration. The supernova evidence has since been confirmed and strengthened by other methods too. Detailed measurements of the CMB, which prefer a flat universe, implying a certain total energy density combined with matter density constraints, shows an energy missing. Dark energy, and observations of the large-scale structure and baryon acoustic oscillations, as well as more supernovae. Everything points to our universe being about 68% dark energy that causes cosmic expansion to accelerate. Astronomers also talk about the equation of state of dark energy, usually denoted W equals pressure over energy density. For a cosmological constant, the simplest dark energy, W equals -1 exactly. Current measurements from Planck CMB, supernovae, BAO, are consistent with W equals -1 within a few percent. This strongly favors the idea that dark energy could be Einstein's cosmological constant reborn. But what is that exactly? Dark energy candidates. Cosmological constant, lambda, versus quintessence. Einstein's biggest blunder? Back in 1917, Einstein considered adding a term, lambda, to his equations of general relativity. This term acts like a uniform energy density filling space, with a repulsive gravitational effect if positive. He set it to a specific value to balance gravity and achieve a static universe, the non-solution to a non-problem as it turned out. After Hubble's expansion discovery, Einstein reportedly ditched lambda, calling it his biggest blunder. For decades, lambda equals 0 was assumed in cosmology. However, as early as the 1980s, some physicists started considering that a small lambda might exist, etc. There were hints, even in the 80s, from the distribution of galaxies and some theoretical considerations that an omega lambda, fraction of density in lambda, could be around zero point 0.7, which sounded crazy until supernovae confirmed it. Now, lambda is back. It's the simplest explanation for dark energy, a constant energy density of the vacuum of space. In Einstein's theory, this vacuum energy would have a negative pressure, equation of state W equals negative, and thus cause accelerated expansion as observed. It fits the data well, a cosmological constant that makes up roughly 68% of the critical density. Omega lambda equals 0.68, and matter, mostly dark, some normal, 32%, gives a flat geometry and matches the acceleration history from supernovae and other probes. If lambda is the answer, then dark energy is essentially the energy of empty space, often called vacuum energy. Quantum field theory indeed tells us that even in a perfect vacuum, particles are constantly fluctuating in and out of existence, virtual particles, and this contributes energy. However, here comes the rub. We'll elaborate in the next part. Naive calculations of this vacuum energy from quantum physics give an astronomically larger value than what dark energy actually is. This is the cosmological constant problem in a nutshell. Why is lambda so small yet non-zero? We'll get to that. Quintessence and dynamic energy. It's possible that dark energy is not a constant at all, but some new dynamic field that changes over time, often dubbed quintessence, after the fifth element, since it's a fifth fundamental component beyond the usual four: baryons, dark matter, radiation. Neutrinos, quintessence, would be a pervasive field like how the Higgs field pervades space that has an equation of state, maybe slightly different from -1, and it could vary from place to place or over time. If, for example, dark energy is quintessence, the acceleration might not continue forever. It could slow down or even reverse if the field evolves. So far, though, observations are consistent with a cosmological constant. No clear signs of evolution in dark energy's strength have been found. But we can only measure so far, billions of years into the past. Supernovae as far as redshift -2, CMB at Z-1100. It remains possible that subtle evolution might appear with better data, or that dark energy might not be constant in the far future. Other exotic ideas. Maybe dark energy is a sign that general relativity breaks down on the largest scales and needs modification, similar in spirit to how modified gravity was considered for dark matter issues. But here for cosmic acceleration. Or maybe it's a hint of an extra spatial dimension, or some feedback from quantum mechanics. Some theories like back reaction, etc. These ideas are speculative. As of now, lambda, the cosmological constant, fits the bill best. Dark energy equals vacuum energy. But this simple answer leads to a huge headache for theoretical physics. The cosmological constant problem, vacuum energy's mystery. We've accepted that roughly 2/3 of the universe is this vacuum energy with a certain density, about 6.5 times 10 to the negative 27 kilograms per meter, or in energy units, about 7 times 10 to the negative 30 grams per meter, or 0.0023 eV per cubic millimeter, an extremely tiny density. Depending on where you cut off your calculation, you might get a vacuum energy density 10 to the power of 120 times higher. If you go up to the Planck scale, or at least 10 to the power of 60 times higher, if you go only to the electroweak scale. The problem: when physicists use quantum theory to sum up the energy of vacuum fluctuations, the result is wildly larger than this observed value. Even the most generous estimates overshoot by many orders of magnitude. This is often quoted as the worst theoretical prediction in the history of physics. Clearly, something is off. Perhaps some cancellation happens between different sources of vacuum energy, ... almost zeroing it out, but leaving a tiny residual. That is what we see as dark energy. But why that particular tiny value? It's a huge fine-tuning problem. To put numbers, observed vacuum energy is equal to 6 times 10 to the negative power, 27 kilograms per cubic meter. Predicted naive, Planck cutoff vacuum energy, approximately 10 to the power of 93 kilograms per cubic meter. Incredible! Which is 10 to the power of 120 times bigger. That disparity, 10 to the power of 120, is 1 with 120 zeros, an unbelievably large factor. It's as if you predicted something should weigh as much as the sun, but it actually weighs as much as a tiny mote of dust. There's no known mechanism in physics that naturally explains this tiny leftover. This is the cosmological constant problem, and it's a big embarrassment. Many ideas have been proposed. Perhaps a new symmetry of nature sets the vacuum energy to zero, like supersymmetry would. But Susie is broken in our universe, and not enough to solve it fully. Or perhaps anthropic reasoning, i.e., B. Only in universes with a tiny lambda could galaxies form and observers exist, so we find ourselves in such a universe, an argument related to the multiverse and string theory landscape. None of these explanations is entirely satisfying to everyone, and it remains an active area of theoretical research. Another facet is the coincidence problem. Why is the dark energy density becoming dominant right around now in cosmic history? Earlier, matter dominated. Later, ... dark energy will dominate even more and dilute matter's significance. We just happen to live when they are comparable. Is that pure coincidence or something deeper? In the lambda CDM model, it's largely coincidence. Though anthropic reasoning might say we wouldn't be around otherwise, if dark energy dominated too early, structure might not form. Still, it's a curious fact. For our meditative purposes, we can reflect that dark energy reminds us how much we still don't understand about basic physics. It's humbling. A term Einstein threw in with little justification might be crucial, but we have no good theory explaining its value. Solving this will likely require a breakthrough in fundamental physics, perhaps connecting quantum theory and gravity. In summary, dark energy could be Einstein's cosmological constant, essentially a property of space, or something dynamic like quintessence, but either way, it's a profound mystery. We observe its effects clearly in the accelerating expansion of the universe. It is stretching space at an ever-increasing pace, driving galaxies apart faster and faster. Billions of years from now, if dark energy remains as is, distant galaxies will fade from view as they recede beyond our horizon at superluminal speeds. Our local group might become isolated in a vast, dark expanse. The universe's expansion is apparently open-ended and accelerating. A very different fate than was imagined a few decades ago. Thinking cosmically, dark energy highlights the poetry of the universe. Even empty space has a secret force within it. It's as if the vacuum, the void, is alive with possibility and influence, quietly steering the cosmos on the largest scales. And we, tiny beings in a small galaxy, have inferred this grand property by studying the flickers of distant supernovae and the whisper of ancient light. Conclusion: the future of cosmic understanding. 3 to 5 minutes. We have journeyed through the darkness, exploring the evidence for dark matter, the hypotheses of what it might be, the experimental quests to detect it, and the startling discovery of dark energy that is propelling the universe's expansion. It's a lot to take in, and if you're listening in a relaxed state or on the verge of sleep, let's gently recap and reflect on the wonders we've discussed. Dark matter recap. Galaxies spin too fast for their visible mass. They'd fly apart if not for some hidden gravity. Clusters of galaxies likewise need extra mass to stay bound. Light from distant objects bends around invisible mass concentrations. The pristine baby picture of the universe, CMB, and the vast cosmic web of galaxies all tell the same tale. There's about 5 times more mass out there than we can see. This dark matter acts like a cosmic scaffold, the glue holding galaxies together and the foundation on which structures formed. It neither emits nor absorbs light and barely interacts with normal matter except through gravity. We've rolled out ordinary dust, gas, stars, and mundane objects. Dark matter is something new, likely a new kind of particle or substance. Leading candidates include heavy, ghostly particles, WIMPs, or ultralight wisps, axions. Among others, scientists around the world are listening for dark matter in underground detectors, looking for its shadowy fingerprints in space, and trying to create it in high-energy collisions, but it remains elusive. The detectors get ever more sensitive, and occasionally nature teases us with hints. A strange gamma-ray glow here, an excess of cosmic positrons there. But the mystery endures. Perhaps in the coming years, a detector deep in a mine will register that faint telltale flash, or a new space observatory will catch the spectrum of dark matter annihilation, or the LHC, or its successor, will produce a new particle that slips out of the detector unseen, tipping us off. Finding dark matter is a quest at the frontiers of knowledge. It's like a modern-day grail hunt for physics and astronomy. And when we finally do identify it, it will open up a whole new realm of understanding. We'll learn about physics beyond the standard model, about how the universe's structure came to be, and perhaps about connections to other cosmological phenomena. Dark energy recap. In 1998, we learned the universe had a plot twist. Instead of slowing down, its expansion accelerated. Dark energy, a smooth, invisible energy filling space, is driving galaxies apart at an ever-increasing rate. It's as if a latent anti-gravitational spring was woven into the fabric of space-time. Today, dark energy accounts for roughly 68% of the universe. The simplest explanation is that it's the energy of empty space, Einstein's cosmological constant reborn. That fits the data, but leaves huge theoretical questions. Why that amount of energy? More exotic ideas of dynamic fields, quintessence, remain possibilities too, and we'll keep testing the behavior of dark energy with future observations, upcoming missions like the Euclid satellite. And the Vera Rubin Observatory will map the universe in detail to see how expansion and structure growth have progressed. Why now? Which will tell us more about dark energy's nature. Solving dark energy likely requires a deeper theory of physics, possibly a unification of quantum mechanics and gravity, or something that emerges from string theory or other advanced ideas. It stands as one of the biggest enigmas in science. The answer will be profound, whatever it is, because it touches on the fundamental properties of space, time, and vacuum. The big picture. It's humbling and awe-inspiring that we, humans, relatively recent newcomers in cosmic time, have been able to piece together that most of the universe is made of something fundamentally different from the matter that makes us. We often call it the dark universe. Not because it's evil or forbidding, but simply because it's literally dark to our eyes and instruments. Yet through ingenuity, we see it with methods beyond eyesight. Through gravity's tug and light's bending and subtle whispers in our detectors. This recognition that we only directly know about 5% of what's out there is both sobering and exciting. It means the cosmic story is far from fully written. Major chapters are missing, but we have clues, and the pursuit of those clues is driving technology and creativity in science. In trying to solve these mysteries, we have built instruments that can detect single photons in a dark cave, satellites that can measure a temperature variation of a few millionths of a degree across the sky, and collaborations of thousands of scientists pooling their expertise. The effort to understand dark matter and dark energy has led to new methods in data analysis, new materials, and even new mathematics. History shows that when we chase fundamental questions, even if the exact answer eludes us for a while, we end up enriching our civilization with innovations and deeper understanding. What does the future hold? Perhaps in the next decade, a combination of upgraded detectors, like a Darwin Observatory for dark matter or a next-gen axion search, will pinpoint what dark matter is. Perhaps a surprise at the LHC or Future Collider will reveal a hidden sector particle. Maybe upcoming cosmological surveys will detect a slight deviation in dark energy's behavior, hinting its quintessence and not a constant, giving us new direction. It's also possible the solution will require a paradigm shift. Something we haven't thought of. A new concept entirely. That's the beauty of being at the frontier. Unexpected discoveries can lurk around any corner. Call to wonder. As we drift off or relax, it's worth reflecting on the poetic enormity of it all. We live in a universe where most of the content is invisible and mysterious, yet its effects orchestrate the dance of galaxies and the destiny of cosmic expansion. There is a profound harmony in how we figured this out by observing gentle lights in the sky and patterns in primordial heat. We uncovered truths about the vast darkness. It's a reminder that even in darkness, there is order and structure and unseen beauty. Feel the wonder of it. Somewhere out there, deep in intergalactic space, far from any galaxy, there are particles of dark matter silently streaming by, and the fabric of space-time itself quietly expanding, doubling and redoubling the distances over eons. These processes are grand and inexorable. Yet here we are, little conscious beings on a tiny planet, able to reason and deduce these cosmic truths. It's as if the universe hid its greatest secrets in plain sight, waiting for curious minds to decode them. In the end, confronting dark matter and dark energy teaches us humility. We don't have all the answers, but also gives us hope and excitement, because there is so much more to discover. The night sky you see, dot, with its sparkling stars, is just the tip of the cosmic iceberg. Beneath lies the invisible bulk, holding galaxies in its embrace and pushing the cosmos outward. As you relax now, perhaps cozied up and closing your eyes, imagine floating in the vastness of space. You are surrounded by dark matter particles flitting through, innumerable, yet silent. They gently pass through you, they really do. Even here on Earth, thousands per second. But you feel nothing. They are that elusive. Far away, you see the glow of a supernova, a sign that a galaxy's expansion is accelerating, carried by dark energy's current. In this serene mental space, you might sense that the universe has deep secrets, but also an underlying peace. It runs on its own grand schedule, with or without our awareness. Let that thought be comforting. There is so much out there, always more to learn, and we are part of this cosmic story. Even in our unknowing, we belong, made of the 5%, but living in the 100%. The dark matter that surrounds our galaxy gently keeps us in orbit. The dark energy that fills space ensures we have a future that goes on and on. We are connected to the whole in ways we are just beginning to fathom. So as we conclude, remain curious and hopeful. The universe is not done revealing its wonders. Perhaps you or someone you know will contribute to unlocking these cosmic mysteries. Until then, we can all gaze up at the night sky in contemplation. In the darkness between the stars, imagine the dark matter halo wrapping our galaxy like an invisible halo of guardians. In the distance of billions of light years, imagine the subtle push of dark energy, like a slow cosmic breath expanding space. Thank you for joining this journey through the enigma of dark matter and dark energy. Feel free to drifting to sleep or continue pondering these ideas in a tranquil state. The universe will carry on its majestic dance, and when you wake, it will still be there, mysterious and beautiful as ever, inviting us to explore deeper. In the words of cosmologist Carl Sagan, somewhere, something incredible is waiting to be known. Sleep well, and may your dreams be filled with stars, galaxies, and the gentle embrace of the unseen cosmos.